Hi guys, this is Carson here. I'm going to be kind of going over, talk about the topic of thermoelasticity and kind of its use in mechanical engineering and some applications for it. So, first thing I kind of want to talk about, just kind of give an overview, is how can we see thermoelasticity, this deformation of materials due to change in temperature. Where can we see this used kind of in the mechanical engineering field? So one thing is you can think about temperature sensors, or thermostats before there were temperature sensors that could read the temperature in the air. We basically used it as a way to tell your heater or AC to turn on. As you can see in this image in the top left, that's kind of the use of where we use thermoelasticity, and we'll get into how that is done through bimetallic strips. But then also we could see that they're also used in toasters for timing. We'll also, we take the advantage of thermoelasticity and the changing of material length and deforming of it to speed up the timer of the toaster as it gets hotter. So, like I said, the way we use this is through bimetallic strips that I talked about. Well, a bimetallic strip is two different metals that are bonded together with two different coefficients of thermal expansion. So you'll have one metal that has a higher thermal coefficient and one that has a lower thermal coefficient of thermal expansion. This will cause some bending of the strip with a change in temperature. So like some of these common bimetallic strips that we could see are brass and steel, copper and steel, and then like for more precise applications we could see invar and brass. But like I said, that's what these bimetallic strips are made of, and the change in the difference in coefficient of thermal expansion is kind of the purpose and kind of the cause of using these bimetallic strips. So this is kind of how they work. So like I said, it revolves around this idea that the two metals that are bonded together have different coefficients of thermal expansion, and when there's a temperature that changes, when there's a temperature change of these metals, the two metals are going to want to expand. So as you can think, if you want to heat up the metals, then they would want to expand, but that's going to be by a different amount because of those different coefficients of thermal expansion. And then because of that, we'll see bending a certain way, and this bending will actually be towards the metal with a lower coefficient of thermal expansion. So this is all because of kind of the mechanics and the math and DEF-BOD's part behind it. Is the thermal strain, which is actually how a material will deform due to a change in temperature, which you can be seen in this equation and we talked about in class. That we have a strain due to some change in temperature times some coefficient of thermal expansion. So if you have a higher coefficient of thermal expansion, then you'll have a higher strain. So like I said, since the two metals have a different coefficient of thermal expansion, or alpha value, the low metal with the larger coefficient of thermal expansion will want to expand more. And like I mentioned earlier, due to this bonding, the strip with the will curve towards the metal with the lower thermal expansion coefficient. And when we actually have this bending, we can actually approximate the radius of that curvature, r, with this equation given here, with t over the difference of coefficient of thermal expansion times the change in temperature. And that little t is actually the thickness of the strip of the two metals. And where we could see this applied, like I said earlier, where I'm going to go more in depth, is, like I said, the HVAC industry. Controlling the temperature in your room is with your thermostat, so that it's able to determine when to turn your AC or your heater on, when to turn your outdoor unit, indoor unit on, and like classic thermostats before we got more advanced with temperature sensors, we had a bimetallic coil, which is just the long version of a bimetallic strip that's wrapped up, and that would bend as the temperature increases. And then when a certain temperature was met, the coil will have bent to a certain amount that will open up or close an electrical circuit that would then control the AC or heater. I was going to try to show you guys a video here, but I can't do it the way that I'm presenting it. So, but if you want to go look at it, you can just follow the PowerPoint that I have attached. But in this little bulb that I have circled, when you turn the heater on, it would actually turn this coil, this apparatus, this coil here, would turn over, and there's a little mercury in this bulb that would float down to here and attach these two cords, which would then turn on the heater. And then as the temperature rises, this coil would kind of unravel until the mercury came back to a settled position in the top, and then it would disconnect between these two wires. Not disconnect, but the connection would no longer be there because the mercury moved, and then your heater would turn off. So that's kind of how we could see it used in one application. And then the considerations for when you're designing these bimetallic strips is you're going to look at the coefficients of thermal expansion, obviously, and then so that your metals have a difference, and so you know which one to place where and how it would bend. The elastic modulus, the thermal conductivity, so how fast the material will change temperature, the durability and the precision, so the durability, how many times can it bend and come back to normal, and the precision is how much is it going to bend due to the temperature change, so that it can either close that electrical current or open it. So kind of an example that I kind of drew out, like, let's say you have a bimetallic strip and your thermostat that controls the heater inside your house, kind of like the one we showed a little bit ago as part of that video. This bimetallic strip is made up of steel and Invar, where here are your two given coefficients of thermal expansion, and so as the temperature rises, the bimetallic strip will bend, turning the electrical current on or off for the heater. In our case, as we can see, as it heats up, it actually rises away from the contact point, which would then turn off your heater. So as the temperature decreases, when it gets to a certain, as it gets colder, it would actually turn on the heater, and then as it heats up, it would turn off the heater. But this is kind of just a visual that you guys can look at that kind of explains how, okay, we can use this DevPod's concept of this thermal elasticity, how it's applied into stuff in the real world. And then kind of to sum everything up, so since we can mechanical deformation can be caused by a change in temperature or this thermal energy that's added to the metals, we can use this deformation to our advantage, like I said. So we can use it to open or close electrical circuits, that then control turning on certain heating elements or AC units, or speeding up processes. So and then as discussed, like we said, they're mostly used for the purpose of passive thermal control. So you're not having to sit there, okay, it's my temperature in my house has reached 70 degrees, let me turn off my AC. It does it all on its own. And then the whole kind of key principle behind these bimetallic strips is this difference in thermal expansion due to having a difference in coefficient of thermal expansion, and that causes this. This is all due to the thermal elasticity that we can see when we have a change in temperature. So I thank you guys for listening. I hope you guys were able to get something out of this. I hope you have a great day. Thank you.